We've reviewed all of the convergence tests and given some guidelines on when to use them. Now we're going to do some practice problems in which we choose a test and see if we can make it work. Before we dive into the problems, let's take a quick look at our guide for how to choose a test that will hopefully be useful to us as we go through this process. We're going to check first for divergence. Then we're going to look for known patterns, geometric, telescoping, or p-series. If we don't have a known pattern, we're then going to look to see if we can compare to a known pattern using the comparison or limit tests. If that doesn't work, we'll look for alternating signs and apply the alternating series test. If we see factorials or exponentials, we can use a ratio or root test. And if our series terms look like an integrable function, we can apply the integral test. These examples aren't given in any particular order. We're just going to dive in and see if we can figure out the right test to use each time. Let's start with the sum from k equals 1 to infinity of k over k to the 5/2 plus 1. We'll do a quick check for divergence. We're looking at the limit as k goes to infinity of our terms, but of course the denominator has a higher power than the top, so that limit is going to be 0, so we can proceed. We'll need to find another test to determine whether or not this actually converges. One approach to take is to notice that the terms of the series, if we get rid of the 1, k over k to the 5/2 plus 1 is less than or equal to k over k to the 5/2, because adding 1 to the denominator makes the entire thing smaller. But that is, of course, equal to 1 over k to the 3/2. This is a p-series. It is a p-series with p greater than 1, which means that it converges. So we know our original sum converges by the comparison test. If we take a look at the sum from j equals 1 to infinity of this rational expression 2j to the 4th plus j to the 3rd plus 1 over 3j to the 6th plus 4, you may be thinking to yourself, I kind of see a p-series in there, and there are a few embedded in there, but making a direct comparison to any p-series is going to be tricky because of the way the parts are combined in this rational expression. However, that's a good instinct to have because we can actually do a limit comparison here. Notice that if we focus only on the top two terms, or the front two terms, they look a lot like j to the 4th over j to the 6th, which simplifies to be 1 over j squared. So what we can do is we can try a comparison using limits to 1 over j squared. If we do that, we're going to be looking at the limit as j goes to infinity of our original expression, 2j to the 4th plus j cubed plus 1 over 3j to the 6th plus 4 over 1 over j squared. Now, of course, we know that when we divide by 1 over j squared, we're going to multiply by its reciprocal, and that's going to give us 2j to the 6th plus j to the 5th plus j squared all over 3j to the 6th plus 4. And then we can do the usual trick. You can either apply L'Hopital's rule 5 times to this, 5 times, maybe 6 times, or you can divide everything by the highest power term. Divide everything by j to the 6th, we're going to get 2 plus 1 over j plus 1 over j to the 4th over 3 plus 4 over j to the 6th. And we can see that all of the terms with j in them are going to go to 0, and we are left with 2/3. And since that is a value between 0 and infinity, we know that this tells us that both the series that we compared behave the same way. And because 1 over j squared is a p-series with p greater than 1, we know that these both converge. All right, let's take a look at the sum from k equals 1 to infinity of 9 over 3k minus 2 over 3k plus 1. So looking at that, there's actually two ways we could handle this depending on what our goal is. If our goal is to just figure out if it converges or not, then one approach would be to notice that this is the same as the sum from k equals 1 to infinity of 9 over 9k squared, and then we have what, positive 3k, negative 6k, so minus 3k minus 2. Hopefully I multiplied that out correctly. And that looks like something we could fairly easily use a limit comparison. If we focus on the first two terms here, we see that this looks like 1 over k squared. So we could do a limit comparison to 1 over k squared, take the limit as k goes to infinity of 9 over 9k squared minus 3k minus 2 over 1 over k squared, which gives us the limit as k goes to infinity of 9k squared over 9k squared minus 3k minus 2, which we know is 1. So this converges by limit comparisons. However, we don't know the value of the thing. And if we look back at the original form, because we have the 3k minus 2 and the 3k plus 1, my instincts tell me this thing might telescope. So let's look at it as if it were potentially telescoping. So we're going to try to rewrite it using partial fractions. So we have 3k minus 2 and 3k plus 1. And we want to rewrite this as the sum from k equals 1 to infinity of some a value over 3k minus 2 plus some b value over 3k plus 1. So to do that, we're going to notice that a times 3k plus 1 plus b times 3k minus 2 has to equal 9, multiplying through by our common denominator. And if we let k be, let's see, negative 1/3, then that gives us a times 0 plus b times negative 3 is 9, which means that b must be negative 3. And if we let k be positive 2/3, then we get a times 2/3 times 3 is 2, so we get a times 3 plus b times 0 equals 9, and we get that a is 3. So our series just became the sum from k equals 1 to infinity of 3 over 3k minus 2 minus 3 over 3k plus 1. And if we begin to investigate now, like we do for telescoping series, our nth partial sum, S sub n, we're going to let k equal 1, and we'll get 3 over 1 minus 3 over, when k is 1, we get 3 over 3/4. That's k equals 1. Let's look at k equals 2. When k equals 2, we have 3 over 4 minus 3 over 7. That's k equals 2. We'll take this out to, so we can see now that the last part of one term and the first part of the next term are going to end up canceling each other out in our telescoping sum. So now if we look at k equals n, we get 3 over 3n minus 2 minus 3 over 3n plus 1. And by our previous reasoning, the 3/7 would have canceled with the first part of the next term. The 3 over 3n minus 2 would have canceled with the last part of the previous term. And so our nth partial sum looks like 3 minus 3 over 3n plus 1. And if we take the limit as n goes to infinity of the nth partial sum, we get 3. And we know that that's exactly equal to the value of our initial expression, which was 9 over 3k minus 2 times 3k plus 1. So now we know two things. We know that this converges, and we also know that it converges to the value 3. So we actually have a value for our sum, which we did not get with the limit comparison test. Okay, if that last one left you feeling a little bit tired, this next one will give you some time to recover. So here we have the sum from k equals 1 to infinity of k to the negative 2/3. We know that we can just rewrite that as the sum from k equals 1 to infinity of 1 over k to the 2/3, turning this into a p-series with a p-value of 2/3, which is less than 1, which means that this diverges. Easy peasy. Okay, since we just did a simple one, now we're going to do one that looks fairly tough. So we have the sum from k equals 1 to infinity of, we've got all kinds of stuff going on here. K to the k over 2 power, 2 to the k, all over the square root of k factorial. So the only test that should jump out to you as potentially dealing with this, because we have the k factorial here and we have all these exponentials, this looks like a prime candidate for the ratio test. It's probably not even worth trying to apply the divergence test, because taking the limit of that thing as k goes to 0 is difficult, to say the least. So we are going to look at the limit as k goes to infinity. Notice that all the terms in this are positive, right? All the terms are positive, which means that we don't have to worry about the absolute value that we usually use in the ratio test. I'm going to leave out the absolute value just because it's one more thing to write. And I'm going to write this as k plus 1 to the k plus 1 over 2 times 2 to the k plus 1 over the square root of k factorial, or k plus 1 factorial, excuse me, over, and then, so that's our k plus first term. We divide that by the kth term, so k to the k over 2 times 2 to the k over the square root of k factorial. All right, multiplying by the reciprocal then, we have k plus 1 to the k plus 1 over 2 times 2 to the k plus 1 over the square root of k plus 1 factorial times the square root of k factorial over k to the k over 2 times 2 to the k. I'm going to group the things that look alike to make our lives a little bit easier. So we have the limit as k goes to infinity. I'm going to put k plus 1 to the k plus 1 over 2 over k to the k over 2 here. And then I have 2 to the k plus 1 over 2 to the k. And then I have the square root of k factorial over the square root of k plus 1 factorial. And we can simplify some of those pieces to make this work for us. So here we're going to have the limit as k goes to infinity. Nothing nice happens in the first piece just yet. The second piece simplifies to just be 2, because the k plus 1 in case we can subtract and get 1. And then over here we have the square root, or we have 1 over the square root of k plus 1, because this can be written, this piece right here is the same thing as the square root of k factorial over k plus 1 times k factorial. So that simplifies to be 1 over the square root of k plus 1. But notice that that is the same thing as k plus 1 to the 1/2. So we have the limit as k goes to infinity of k plus 1 to the k plus 1 over 2 minus 1/2. That minus 1/2 comes from this piece, the square root of k plus 1 in the denominator, over k to the k over 2 times 2. All right. Simplifying that exponent now, I'm really having a hard time writing that arrow. We get k plus 1 to the k over 2 over k to the k over 2 times 2. Since the top and the bottom have the same exponent, we can write them together. So we get k plus 1 over k to the k over 2 times 2. And of course, I can move the 2 to the front of the limit if I want. I'll do that now. 2 times the limit as k goes to infinity of, simplifying this, I have 1 plus 1 over k. And I'm going to write this as to the kth power, all to the 1/2. And the reason I did that is because this limit, or this term in here, is hopefully something you recognize. That is e. So we get 2e to the 1/2, which is, after all that work, greater than 1, which means that our series diverges. All right, let's look at this next one. After that last one, this one's going to appear really easy. We can see by the way this is written that this is an alternating series. This -1 to the n term gives us an alternating series. And so we have to remember that we have the alternating series test, which tells us that as long as this term, 1 over n to the 2/3, not 2/2, as long as that is positive and decreasing, which it is, as n gets larger, that's certainly going to get smaller and it will never be negative. If the limit as n goes to infinity is 0, then we have a convergent series, and that is in fact the case here. So this converges very straightforwardly because it is alternating. It converges by the alternating series test. But notice that the sum of 1 over n to the 2/3 diverges because that's a p-test with p less than 1. So what we actually know is that this original series converges conditionally. In other words, without the alternating part, it fails to converge. But once we make it alternating, we get a convergent series. All right. This one looks maybe a little similar to one of the limit comparison ones that we did earlier. But if we look at the terms here and we think about taking the square root of 9k to the 8th, that looks something like 3k to the 4th, which means that our first terms on the top and the bottom are pretty similar, which is making me a little suspect about this limit. I want to look at the limit of the terms first. I'm going to use the divergence test to see if it's worthwhile pursuing a limit comparison test on this guy. So what I'm going to do is I'm going to divide everything by I'm going to multiply everything by 1 over k to the 4th, which is the same as 1 over the square root of k to the 8th. So when I do that, I get 2 plus 1 over k to the 4th. And then on the bottom, when I bring this inside, I get the square root of 9 plus 2 over k to the 8th. Well, that limit, because these terms go to 0, becomes 2 over the square root of 9, which is of course 2/3, which is not 0. not 0, which means that this diverges by the divergence test. So no need to look any further than that. All right, let's look at this next one. We have the sum from k equals 1 to infinity of a rational expression raised to the kth power. Now, this is one where we might not want to try the divergence test right away because that limit is pretty rough to take. But because we have this kth power here, we can think about using the root test. So the root test tells us to look at the limit as n goes to infinity of the nth root of the nth term, the absolute value of the nth term. But notice these terms are positive. All of those terms are positive because k is positive, so we don't have to worry about the absolute value, so we can just write this as n over 2n plus 3 to the nth power. And of course, the nth root and the nth power cancel each other out. We get the limit as n goes to infinity of n over 2n plus 3, which is 1/2. And because that is less than 1, we know that this thing is behaving sort of geometrically for large values of n, so this converges by the root test. Okay, in this one, we see we have k powers on both the top and the bottom. So while it doesn't initially look like a geometric series with a clear r value, I think we can do a little bit of rearranging here. I am going to let the bottom, I'm going to split the bottom up into 2 to the 2k times 2, because of course I can add exponents. And then that becomes 5 to the k over 2 to the 2k is the same as 4 to the k times 2. So what we have here is 1/2 times the sum from k equals 1 to infinity of 5 over 4 to the k. Well, that is very obviously geometric. It is geometric with an r value of 5/4, which is greater than 1, so this diverges. Final example, we have the sum from k equals 3 to infinity of the natural log of k over k. So we can see that the limit as k goes to infinity of this guy is the same as the limit as k goes to infinity of taking derivatives 1 over k, which is 0. So it has a chance to converge. So we need a test. Nothing obvious jumping out to me, except that I notice that if I look at the function ln x over x, that's fairly easy to integrate. So I'm going to use an integral test. I'm going to examine the integral from, we can actually go from 3 to infinity, since that's our limits on our series of our function. So that is the limit as b goes to infinity of the integral from 3 to b of ln x over x dx. But of course, a straightforward substitution, u is ln x, du is 1 over x, gives us that this is the integral now from the natural log of 3 to the natural log of b of u du. I forgot to write my limit out here, so I will put it out here. The limit as b goes to infinity of that. Then that's going to be the limit as b goes to infinity of u squared over 2 from ln of 3 to ln of b, which is the limit as b goes to infinity of the natural log of b squared over 2 minus the natural log of 3 squared over 2. But this goes to infinity. So this integral fails to converge which tells us that our original series does not converge as well. Now, it's entirely possible that you were cleverer than I was at the beginning of this, and you notice that since ln of k is always bigger than 1 for k bigger than e, that ln k over k is actually larger than 1 over k, which is, of course, a divergent p-series. So we could have worked a little less hard and gotten the same result.